Let's continue. We have here a one-dimensional consolidation test. So this is a figure. We have simulation of 1D field consolidation in lab. Say we have here a soil sample in the field, and we're going to look for this undisturbed soil specimen, which has a diameter of range 50 to 75 millimeter and height 20 to 30 millimeter. And this is the representation, no? If we're going to enlarge this one, muna siya. And notice that in the loading, no, when loaded, no, in increments. So we have here an original h, the height, and the initial void ratio. And due to this external load, no, we have the loads, then naatay change in void ratio because the volume has changed, then allowing full consolidation before next increment. Then this is the result. Then from here, then unloading increments. So notice that nibalik siya sa original nga almost, no, volume. So we have here from there, no, we can plot the void ratio pressure. So typical plot during loading. So we have here a loading and unloading, no, condition. The plot during loading and again and reloading. So we have here loading, no, until such time there is this permanent deformation. Then unload nimo siya, and then again reload. Pag unload nimo, there is this elastic recover, no. Then pag reload nimo, this is the result of the deformation. Sorry for the not so good kanang klaro, no, dili kay siya klaro. But calculate the height of the soils H sub S in the soil specimen using the equation where this is the height of the solids in figure 10.11. So this is the formula, no. W sub S is the dry weight of the specimen over Ag sub S times the unit weight of the water. Area of the specimen times specific gravity of the soil solids times the unit weight of the water. Then the initial height of the voids is H sub V is equal to the original height minus the height of the after loading, no, where H is the initial height of the specimen. Calculate the initial void ratio E sub O of the specimen using this equation. This is in the laboratory, no. For first incremental loading, sigma sub 1, total load over unit area of the specimen, which causes deformation of delta H1. Calculate the change in void ratio as this. Now, delta H1 is obtained from the initial and the final reading of the loading. It is important to note that at the end of the consolidation, total stress sigma 1 is equal to the effective stress sigma prime 1. Calculate the new void ratio after consolidation caused by the pressure increment as this formula. No? Original minus a change in the void ratio for next loading, sigma sub 2. Note that sigma sub 2 equals the cumulative load per unit area of the specimen which causes additional deformation. Delta H sub 2, that the void ratio at the end of the consolidation can be calculated as this formula. Alright, so we have here an example. Data obtained from a laboratory consolidation test are tabulated as follows. So we have here test points up to 6, then a effective stress, and the total change of height during the loading stage. So we have here the properties of the soil is specific gravity is 2.7. The initial thickness of at zero pressure is 22.5 millimeter, and W is the moisture content at the beginning of the test, which is equal to 0.78. We are asked to plot the void ratio lag effective stress curve. So from here, we're going to use SE. This is supposed to be SE is equal to WGS, but this is saturated, fully saturated, so that the S, or the degree of saturation, is equal to 1, and thus the original void ratio is equal to the moisture content 0.78 times the specific gravity 2.7 at zero pressure. Now to plot the void ratio versus the lag effective stress, we have here a ratio and proportion. So we have here the original void ratio at zero pressure. So manang nabutang siya dire. Zero pressure. Then to find for the preceding succeeding void ratios, this is the change in the void ratio. This is original void ratio minus sigma 1 over 0.23. This is the change in height, or delta H is equal to 1 plus the original void ratio divided by the total height, diba? Or this is actually the volume, but the volume also corresponds to height, no? So that we can get the first void ratio, so on and so forth. So ano ni siya, hangtod, then we can plot the void ratios versus the this stress, effective stress. We have here a terminology, the effect of stress history. We have here normally consolidated soil and the over-consolidated soil. Normally consolidated soil is a soil which had not been subjected to pressure greater than the present existing pressure. Portion of AB of loading and unloading curve represent the soil in normally consolidated condition. While overly consolidated soil is said to over-consolidated if it had been subjected in the past to a pressure in excess of the present pressure. The soil in the range of CD loading and unloading curve, when it recompress, represent the over-consolidated condition. So we have here a figure, void ratio versus the lag stress. So the stress state, sigma sub 2 represent normally consolidated soil. So this part here is the normally consolidated soil, while the above part is the over consolidated soil. No. The stress state sigma sub 2A and sigma sub 2B represent the over consolidated soil. This part, no, kaning dagko nga void ratio. And this part here is the normal consolidated soil. We have the pre-consolidation pressure. It is the maximum effective stress experienced by a soil in its stress history or past experience. We have here a figure, no? For example, this figure for the soil loaded along a recompression curve AB, the effective stress close to B will be the pre-consolidation pressure. So this part, no, here, because it is the maximum effective stress experienced by a soil in his history. If the soil is compressed along BC and loaded along CD, unloaded, compressed then unloaded along CD, and then reloaded along DC, the effective stress close to point C will be the new pre-consolidation pressure. So we have here determination of pre-consolidation pressure by Casagrande construction for determining the pre-consolidation stress. So we can use a tangent line. No? Say this is the curve of the void ratio versus the effective stress. This is the curve. Then if try to draw a tangent lines here, then select the common point, no? And that is the point of pre-consolidation stress. We have the ratio, the over consolidated consolidation ratio, OCR, is defined as the ratio of the pre-consolidation to the present vertical effective stress. Now, this is indicative of the position of soil away from the normal consolidated line. OCR is equal to normally consolidated soil. Note that the soils having higher over consolidation ratio are less compressible, and they show elastic behavior to a certain extent. Having higher, so greater ang iyahang pre-consolidation pressure. So the overly consolidation pressure is equal to 1 if normally consolidated soils. So the pre-consolidation pressure is equal to the vertical effective stress. So we have here the compressibility properties. So we have here the curve. So this is the recompression line. Then this part is the normal consolidation line. Then we have the C sub R, or the recompression index, as loading, no, as loaded, the stress increases while the void ratio decreases. Then this is the compression, no? This part here is the compression part. So we have a compression index. Then after loading, no, this part, then we unload the soil so that the effective stress decreases, but the void ratio increases because of swelling. So we have this part has this swelling index. No? This is this unload part, this one, unloading. And the coefficient of compression, or the compression index, C sub C, is equal to 0.009 liquid limit minus 10. This is the derivation. So it is a slope of the normal consolidation line in a plot of void ratio logarithm of effective stress, E lag, or can be found to be equal to 0.009 liquid limit LL minus 10. So we have different compressibility or compression index of the different soil, no, or region of applicability. So this different equation of compression index is applicable only to this region of applicability, no. Like this, for the first equation, 0.007 element 7, according to Skempton in 1944, is for the remolded clays, no. The swelling index is given as equal to this void ratio 1 minus void ratio 2 divided by log 10, the corresponding effective stress at void ratio 2, no, over the corresponding effective stress at void ratio 1. So this is the swelling, no. So swelling index is for the unloading part of the soil. And we have the coefficient of compressibility in this ratio. It is the slope of void ratio versus the effective stress for a given increase of effective stress in void ratio versus effective stress. This can be applied, no, later sa equation. And we have here the coefficient of volume compressibility, or M sub V. This is equal to delta E over 1 plus the original or the initial void ratio times 1 over the increase in the effective stress. It is the ratio of change in volume of soil per unit initial volume due to unit increase in effective stress. So we have here a representation of the to compute for the settlement. Okay. From here, we have derived an equation for the normally consolidated soil. No, for the case of normally consolidated soils, this is the equation. Delta H, or this is the settlement, is equal to the coefficient of compression, or this is compression index, which is equal to 0.009 LL minus 10 in the previous equation that we introduced, over 1 plus the initial void ratio times H. This is the height of the soil that we are going to determine the settlement. Log 10, this is the vertical effective stress, plus the change of stress. This is external load over the effective stress. For overly consolidated soil, we have here for case 1, no? For case 1, if the vertical effective stress plus a change in stress is less than or equal to the effective stress, then this is the formula. For case 2, if it is greater than, then this is the formula. We have also the secondary consolidation settlement. After the primary consolidation settlement, then naatay secondary consolidation settlement. This is the formula for the secondary compression index, or C sub alpha. No, this one. And to obtain the prime, no? This is the formula. Then the equation to be used for the secondary consolidation settlement for the settlement is this one. The C sub alpha prime H log T2 over T1, which is this is time dependent kind of settlement that we discussed now in the previous slide. T1 is a time for completion of the primary settlement, and T2 is a time after completion of the primary consolidation. Alright, we have here an example problem. A rigid 3-meter square footing is constructed over a loose sand layer as shown on the figure. So this is the figure. We have a load 710 kilonewton. Then this is loose sand and a clay. We are trying to get the settlement at the clay layer, no? It carries total load of 710 kilonewton. The total distributed load from the top to the bottom of the clay is 6.08 kPa. Compute the elastic settlement of the 3-meter footing if, so this is the base, no? This is the B, 3-meter footing. If the Poisson's ratio of the soil is 0.32 and the modulus of the soil, elasticity of the soil is 16,000 kPa, the influence factor is 0.88. So we are now given a 0.88 elastic settlement, meaning this is for immediate settlement, no? For the compute elastic settlement, meaning this means the SI, or the immediate settlement. Remember, we discussed, or in the previous slide, settlement, or this is SI. No, the formula for the SI is this equation. Diba? Remember this equation. So the Q, this is the pressure due to the load at the footing. So meaning that is this should be the pressure or stress. So this should be force over area. Remember, 710 is this load divided by the area, which is 3 by 3. I guess this footing is a square footing with 3 by 3 footing, no? Square footing. So, mo na siya, no? Is equal to 78.79 kPa. And substitute the values. We solve this one. This is given because this is B, no? The base of the footing. Times 1 minus, this is also given. This one is given. And the influence factor is also given, which is equal to 0.88 in the problem, over the modulus of elasticity of soil 16 thousand. So the immediate settlement is approximately equal to 12 millimeters. This is for the computation of letter A. For letter B, compute the primary consolidation settlement of the clay layer if it is normally consolidated, whereas to determine the primary consolidation settlement. So remember the formula, this one, di ba? For the primary consolidation settlement. But first, we have to get the effective stress. This one. This one is the effective stress. Effective stress. So, at clay layer, at the middle of the clay layer, man. So, our atong target is at the clay layer. So, to get the effective stress from here up to this middle part of clay, no? So, to get effective stress is 16 times 5.2. This one, no? 16 times 5.2 plus 18, because this is the the saturated unit weight at this part, minus 9.81 for the pore pressure, pore unit weight of the water, times 2, because this height here is 2, and plus 20 minus 9.81 times 2, the middle of at clay layer. This one, this formula. So that the answer for the effective stress is 119.96 kPa. To solve for the coefficient of compression or compression index, we have the formula 0.009 LL. This is LL minus 10. I think liquid limit is given as, alright. This one, in the figure, this should be liquid limit. This is not a specific gravity. No, this is liquid limit equal to 45. So that's why we have here 0.00945 minus 10, which is equal to this. No, and substitute in the formula. And this, we have here a delta P. This is given in the problem, which is equal to 6.08. This is the total distributed load from the top to the bottom of the clay. Change of pressure. So, diha ni siya ibutang delta P 6 point total distributed load from the top to the bottom of the footing. Then substitute. The initial void ratio is also given as equal to 0.6, no, in the figure. Then substitute the values so that the primary consolidation settlement is equal to 17 millimeters. Next one for the letter C is compute the total consolidation settlement after 5 years. No? So we are asked for the total consolidation after the completion of the primary consolidation settlement. The time for the completion of the primary settlement is 2 years, and the secondary compression index, or this is C sub S, no? In the formula earlier is 0.02. So 2 years to 5 years, no? After the completion of primary settlement is 2 years time after, then pila daw ang total consolidation considering the immediate settlement plus the primary consolidation settlement plus the secondary settlement. Muna siya atong i-add, no? To get the total settlement after 5 years. So first is, this is the formula for the secondary settlement, no? And to get for the void ratio at the secondary settlement after the primary settlement is the original initial void ratio minus a change in the void ratio. And the change in the void ratio is this formula. Now, C sub C is computed as 0.315 this in this slide. Log this is the effective stress that we computed earlier, 119.96 plus the distributed pressure now at the footing, 6.08 over the effective stress. So this is the change in the void ratio. So from here, balik ka ani nga formula to get this value, no? That is the initial void ratio 0.6 as given in the problem minus the change in the void ratio 0.0067. So this is the result, and substitute the value for the coefficient of settlement, or as given the problem, secondary compression index is 0.02, no? 0.02, or that is, that is C sub alpha. Sorry, this should be C sub alpha. Is given the problem as 0.02, and H, this H here, this is the height, total height of the clay, which is given in the figure 4 meters. This one, no? 4 meters. So, mo na ang 4 over 1 plus, as given the formula, 1 plus E sub P, which is we computed as 0.5933, log T2 over T1. T1, this is the years, now the time in years after the primary consolidation settlement. Then we are asked to determine the settlement after 5 years. Then manang 5, your T sub 2. So that your settlement, secondary consolidation settlement, is equal to 20 millimeters. So that the total settlement after 5 years is this summation of the immediate settlement, or SI, the the primary consolidation settlement, the C sub C, and the secondary settlement, which is the C sub S, no? So that the answer is 49 millimeters settlement of this specific footing. So we have here a figure, no, represented by this type of settlement. So remember that the immediate settlement is instantaneous, no? Grabe ka dali nga settlement. So this is the figure representation. So it is a settlement due to plastic compression arising out of readjustment of soil particles at constant effective stress. It occurs after primary consolidation settlement. So this is the the representation of the settlement. The primary consolidation, and after is the secondary consolidation. We have here another example problem. A 2.1 meter layer of clay is buried beneath a 3 meter stratum of very compact granular soil. So this is, the granular soil is 3 meter and the clay is 2.1 meter. Compact sand underlies the clay. The layer of granular soil is composed of material having a unit weight of 20.46. So the unit weight of this one is 20.46 kilonewton meter cube. So forgive me sa akong penmanship because I only use the mouse. And the clay weight is, unit weight is 16.52 kilonewton per meter cube. A laboratory compression test on a sample of the clay indicates a compression index of C sub C here is 0.4 compression index. No, this is C sub C. A natural void ratio of 1.3. E sub 0 for the original void ratio is 1.3 at clay. A plant building loading will cause 26.38 kPa stress increase, no, at the middle of the clay layer. So there is a delta change of stress, that is delta P is equal to 26.38 kPa. Stress increase. What amount of primary compression occurs? Primary compression occurs in the clay for the indicated conditions. We are asked for the primary consolidation, no? Primary compression. So first is we have to determine the effective stress at the middle of the clay layer, no? So to get the effective stress at the middle of the clay layer is to solve for the effective stress. So I believe, no, you are familiar with computing the effective stress at a layer of soils. So for effective stress, unit weight of the granular soil, that is 20.46 times 3 plus 16.52. So wala siya giingon, no, if it is um saturated unit weight, but just the unit weight of the clay times 1.05. So this is the effective stress result, and the change delta P is given the problem equal to 26.38 when there is a footing, no, bland building footing. So the formula for the primary consolidation compression is equal to the compression index times H over this is the compression index given as equal to zero point 0.4 times height of the clay over 1 plus the initial void ratio lag effective stress plus the change in the increase of the pressure over the computed effective stress, no, according to the given. And then substituting the values, no, from this formula in this formula, then we can get the the settlement, no, the primary consolidation settlement.